Okay, so this is going to be Physics 111, Chapter 14. Chapter 14, we're going to be talking about fluids. So when we talk about fluids, we're really talking about liquids and gases. So both liquids and gases are considered to be fluids. Now there's three kind of states. You have your solid state, your liquid state, and your gas state. Let's look at the video to see the difference between them. Put this down.
Here, a microscopic view of a solid is shown schematically. In a solid, molecules are held close together in an orderly fashion with little freedom of motion.
So the bonds between the solids are strong, with no room for any motion. When we talk about liquids,
this figure represents a microscopic view of a liquid. Molecules in a liquid are close together but are not held so rigidly in position compared to a solid and can move past one another.
So there are bonds that exist between the liquid. They're not very strong bonds, but there are bonds that goes between the liquids. That's the reason you can form it to any shape that it contains. The third one is gas.
A microscopic view of a gas is shown schematically. In a gas, the molecules are separated by distances that are large compared to the size of the molecules.
So the distances between molecules in the gas are almost non-existent. So that's why you can have gas just go everywhere. So solid, liquid, gas. Now let's talk about the density of the material. Now we're gonna give the density our little raw, Greek letter rho, as you will. Which is defined as your mass per unit volume. This little v with the little wings that I have, that's your volume. M is your mass, and your density is your rho. So your density of the material is your mass per unit volume. That means in terms of units, it's going to be kilograms per meter cube. Now, what is volume? So let's talk about volume. Your volume is defined as your length multiplied by your width multiplied by your height. It's your length multiplied by your width multiplied by your height. Usually, it's going to be meter times meter times meter, which is going to equal to meter cube. Now, let's go back to our little slides. So your density of the material is your mass per unit volume. And because it's your mass per unit volume, your mass is in kilograms, your volume is in meters square, meter cube, so it's usually in kilogram per meter cube. Now, often densities are given as gram per centimeters cube as well. So here's some densities of some substances that we're going to be looking at. The main one we're going to be looking at right now is your water, which is going to be your 1 times 10 to the third power kilogram per meter cube. Let's take a look about a video about the density of water.
Water has the peculiar property that its solid ice form is less dense than its liquid form. Thus, ice cubes float in water. Most substances like benzene, shown on the right, have a solid form more dense than its liquid form. Thus, the solid form sinks to the bottom of the liquid.
So when you have a substance that's less dense than the liquid, kind of like the one we had on the right, Yeah, like ice, it will float. If you have substance that's going to be more dense than the liquid, it's going to sink. Now, talking about volume. For a rectangular box, your volume is your length times the width times your height. So supposedly we have a box that's 1.3 times 0.6 times 0.3. What is the volume for this box? Well, let's take a look. So your length over here is 1.3, your width is 0.6, and it's 0.3 meters for your height. So this little example that we have, your length is 1.3, your width is 0.6 meters, let's look at the meters, and your height is 0.3 meters. That means your volume, which is your length times your width times your height, is going to equal to 1.3 multiplied by your 0.6 multiplied by your 0.3. So you get 0.234 meter cube. So in our little example, this bathtub over here has a volume of 0.234 meter cube. Now, calculate the mass from the volume and the density. All right. So over here, we were looking for the volume, and we got the volume. Now we need the mass. Now, we said that the mass, the density, is going to equal to your mass divided by your volume. That means that your mass is going to equal to your rho multiplied by your volume, which for water, we said it was, let's look at our little table. It was 1 times 10 to the 3 power, 1,000 kilogram per meter cube. So your density for water is 1,000 kilograms per meter cube. So your density is going to be 1,000 multiplied by your volume, which is 0.234 meter cube. So your answer is going to be 234 kilograms. If you actually looked at the units for this, what's the units for this one? This one is going to be in kilograms. This one is going to be in kilograms. So this one's going to be kilograms per meter cube. And this one's going to be in meter cube. So both meters cube cancel out. So what you're going to have left, kilograms. Now, let's talk about pressure. Now, imagine if you go out to the beach on the sand and you get your finger and you stick it in the sand. What's going to happen? Well, chances are that your finger is going to actually go inside deep in the sand. Now, let's say you take your whole hand, you open it up and try to put it on the sand. What would happen? More likely, your hand would not go inside the sand, although you're actually getting more pressure. So that gets us down to the pressure. The pressure is a force from your finger that you're putting on per area that you're actually trying to do the pressure at. So the pressure on a surface is perpendicular force per unit area. So your pressure is going to equal your F over A, your force per area. So let me go ahead and write this down. So now your pressure is going to be a P. Pressure is going to be your force per unit area. Now, your force in units is going to be in newtons. This is your force. This is your area. Now, this is going to be in newtons. And your area, which is your length times your width, so it's meter times meter, which equals to meter squared. So your Newton over meter squared, that's what we call your Pascal. So your Pascal usually is how much newtons per meter area. So again, your pressure on a surface is a perpendicular force per unit area, which is F over A. Your force is in newtons. Your area is in meter square, so it'd be force per meter square. Again, do not confuse force with pressure. Your pressure is how much force you do on something per area. So let's look at a question, shall we? A tire pump has a piston whose cross-sectional area is 0.001 meters square, and we apply a force of 150 newton to the piston. Find the pressure on the air in the pump. So let's go ahead and write the equation down for the pressure example. All right. So you got an example over here. So we got an area of 0.001 meters squared with a force of 150 newtons. So 0.001 meters squared, and your force is 150 newtons. And we want to find the pressure. That means your pressure is, again, your force per area, which is 150 newtons divided by 0.001 meters squared. So your answer should be 1.5 times 10 to the fifth power newtons per meter squared. Or basically 1.5 times 10 to the fifth power pascals. Or if you want to do it in kilopascals, it'd be 150 kilopascals. Let's check if our answer is correct. And like we did, it was correct. It was your force over area, which is 150 divided by 0.001, so it's 150 kilopascals. Let's do another example, shall we? Before a storm, people in a house close doors and windows so tightly that the air pressure inside remains at 101 kilopascals. Even when the outside pressure has fallen to 98 kilopascals. How much force acts on a window 80 centimeters high by 120 centimeters wide? So you got your initial pressure, which is 98, and your final pressure is 101. So let me just go back. What was that example? This is 5.8. So you got your pressure final, which is 110 kilopascals, and your initial pressure was 98 kilopascals. What else do we have in the question? And then we got a window. Your width, I'm just gonna write down width, is 80 centimeters, which means it's 0.8 meters. Your length is 120 centimeters, which means 1.2 meters. I don't know what that little dot came from. That means your area, which is your length times your width, equals to 0.8 multiplied by 0.12. So it's 0.96 meters squared. And we need to find the force. How much force acts on a window. So we need to find the force. Now we know that the pressure equals to your force per area. You change your pressure equals your force per area. That means your force is going to equal to your change of pressure multiplied by your area, which is going to equal to 101 minus your 98 multiplied by your area, 0.96 meters squared. So this is going to equal to, this by the way, it's 101K minus 91K, so it'll be 3 times 10 to the 3 power pascals multiplied by 0.96, so it's 2,880 newtons. Awesome. Now, let's talk about the buoyancy force. Now, the upward force exerted on an object immersed in a fluid is called the buoyancy force. So, supposedly, you get a container that has some kind of liquid, let's say water, okay? Now, when you have an object on here, there's inside the liquid, there's gonna be pressure going in to that object from all kind of directions. So pressure. You're gonna have force by that area from all kind of directions. So let's say you have the object right over here. Now, actually, let me just make this a little bit bigger. Okay, here, and let's say this is over here. Now, when you have an object in there, the distance that's going in from the top of liquid to the top of the object, that's your H. And let me get a different color on this. The object dimensions, which is gonna give it your distance D. Now you're gonna have 2 pressure points usually, one over here, one over here, which is you're gonna have, we're gonna call this one P1 and P2. So your pressure is acting, so your pressure is acting in all directions including up. Now again, remember that your pressure is going to equal to your force per area, which is, that means your force that you're going to have is going to equal to your pressure multiplied by that area. So your net force that you're going to have is going to be your F2 minus F1. Your F2 is going to be your pressure of 0.2 multiplied by the area of that object minus your pressure 1 multiplied by the area of that object. Which, if you actually factor the area out, what you're going to have? You're going to have your P1 minus your P2. Now, what is the area? Well, we said the area, we defined it as your length times your width, which means the area, if each side, we're going to give it, I don't know, the letter D for distance. Actually, this is actually a little bit too big. Here, that's better. So that means your area is going to equal to D squared. Now let's take a look at point 1, the pressure at point 1. Let me just get a different color for that. So the pressure at point 1 is going to equal to your rho multiplied, here's your point 1 right over here. So the pressure that's going to happen is going to equal to your rho multiplied by your height multiplied by the weight, by the gravity. So your rho hg, again, rho is density, h is your height, and g is your gravity. Meanwhile, if you look at the pressure at the second area, it's really going to be it's going to be your, let me pressure a second, it's going to be your density of the liquid that you're in multiplied by your gravity multiplied by the distance, which is going to be, in this case, for this, is going to be your h plus your d. H plus d. That means, and what color do we have? We have a black, so let's go back to black. That means your net force is going to be your F2, well, we said your area multiplied by P1 minus P2. So that's going to equal to D squared multiplied by rho Hg plus rho dg plus minus, should we subtracting? I'm sorry, this is going to have to be P2 minus P1. I'm sorry, here it is. Let me just fix that. That is P2 minus P1. So let me just, I just noticed that I flipped them by accident. So your net force is going to be your D squared multiplied by your rho Hg plus your D rho G minus your rho dg multiplied by your, well, we got D squared on there. You see, the object that you're going to have on here is going to have a buoyant force going up, and you're going to have an, well, let me just go like this. Gravitational force. So really, let me just write it over here. So you're going to have, it's your liquid. So you're going to have your buoyant force going on top and your Fn, the one we're trying to on bottom. So your buoyant force that we're trying to see is going to be your pressure multiplied by your area, which is going to be your d distance multiplied by the pressure multiplied by g multiplied by d squared. So you got d squared multiplied by d, so that's d cubed rho g. And again, let me just label this down. Your d cubed, that's your volume. Rho is your density. And g is your gravity. Now, we notice that we have d squared, d cubed rho. Remember that your density was your mass per unit volume. That means your mass is your rho multiplied by your volume, which is, that's what we have over here. So your buoyant force is going to equal to your volume multiplied by your rho multiplied by your gravity. Now your Fn, that's going to equal to your mg, which is the weight of the liquid displaced. And again, Fn, that's your net upward force. So let's do an example, shall we? Let's say you have an object weight that weighs outside the water 10 newtons. And in water, there's going to be 2 newtons. That means use your object and it's going to immerse in some kind of liquid in water, right? So your weight 1 is going to be 10 newtons. Your weight 2 is going to be in your 12 newtons. That means your buoyant force is going to equal to, so this is going to be 2 newtons, not 12. That means your buoyant force is going to equal to 10 minus 2, which is 8 newtons. That means you got 10 newtons going down here, and you got 8 newtons going upward with the buoyant force. Now the buoyant force is again your volume in the water multiplied by rho multiplied by gravity. Oh, by the way, I forgot to say, find the water volume. So your volume in the water is going to equal to your buoyant force divided by your rho multiplied by g. Your buoyant force, the one we found, was 8 newtons divided by your density of the water was 1,000 multiplied by 9.8. So we should get 8.2 times 10 negative 4 meter cube. Wonderful. Now, so basically, when you have, again, let me get my container. This is a funky looking container. And here's your object, and you got your water in there. So again, you got your what's that, P1 over here, and you got P2 over here. So your P2A, which is your F2, is going to be F1 minus rho times V times H. So this one's going to equal to rho Pg. So it'd be your P1 multiplied by the area. I'm sorry, it's added. Plus, you got your weight going down. There was going to be rho Vg. V again for your volume. And your volume is going to be, and again, this is going to be your area multiplied by your height. So P2A is going to equal to P1A, pressure 1, multiplied by the area, plus rho AHG, which means we can go ahead and cancel our little areas over here. So your final pressure is going to equal to your first pressure plus rho GH. That means your delta P, which is your difference into your pressure, is going to equal to rho GH. Now, your atmospheric pressure is 1.01 times 10 to the 5th pascals. Your water pressure is 1 times 10 to the 3rd, 1,000 kilograms per meter cube. And now, so you got the force, let me just get a different color. One going down here and one taken up there. This one's gonna be, again, P1A1, this is gonna be to P2A2. So your buoyant force, get a different color, is going to equal to P2A minus P1A. And like we just saw a little while ago, that's going to equal to P2 minus P1 multiplied by your area, which is going to be rho multiplied by your volume multiplied by your gravity, which is right over here, the buoyant force. Actually, let me go ahead and write in the buoyant force on this one. That way it'd be more clear. Now, your density multiplied by your volume, again, we said that was your mass. What is that? That's the mass of the displaced fluid. That means your buoyant force is going to equal to the weight of the fluid. Okay? So let's take a look. So basically, the pressure at any point in a liquid depends on the distance below the surface, which is your distance, we got it as h in my notes a little while ago, multiplied by the gravity multiplied by your depth. Depth is the distance below the surface. So the buoyant force is always an upward force because the pressure underneath the immersed object is greater than the pressure above it. So let me go ahead and show a little video about that.
This demonstration will show how the buoyant force on a submerged object is related to the amount of water displaced by the object. This aluminum cylinder and pail hang from a scale, which shows the total weight to be 29 newtons. We'll lower the cylinder into this water container, which has an overflow spout. When the cylinder is submerged, the reading on the scale decreases to 20 newtons. All water displaced by the cylinder will flow into a beaker. If we pour the water that was displaced by the cylinder into the small bucket hanging from the scale, how will the reading change? This demonstrates.
Now, how would the reading change? The reading would stay the same. Let me just go get the video, 1 second. Okay, we uploaded the second video. Let's look at it. So the question was, and let me look at the question. How will the reading change? Will it be less than before, more than before, same as before, or can't tell from the current information? Think about it for a second. Now let's go ahead and watch the video, see if it matches your answer.
The scale now reads the same as before the cylinder was lowered into the water. The buoyant force on the cylinder is equal to the weight of the water displaced.
So the buoyant force equal to the weight of the displaced water. All right. So we looked at the mass density of a substance again, which is going to be your mass per volume, which is going to be kilogram per meter cube. So let's say we have a question. Here's some masses again. Here's a table of mass densities of common substances. So we said the body of a man whose weight is 690 newtons contains about 5.2 times 10 negative 3 meter cube of blood. Find the blood's weight and express it as a percentage of the body's weight. So we got 690 newtons. We see newtons, you know that is going to be your force. Your 5.2 times 10 negative 3 meter cube, you know that's going to be your volume. So let's just look. This example says example 1. So I don't know. I'm just going to go with what we written down. So this is going to be example 1. So your force is 690 newtons and your volume is 5.2 times 10 negative 3 meter cube. We want to find the blood's weight. So we want the weight. Let me just write this down. W-E-I-G-H-T. Now, in order to find the weight, we define it as before as your mass times gravity. But we don't have the mass. So in order for us to solve for the mass, we use rho equals m over v, which means your mass equals your rho multiplied by your volume. Now, what is your density for the blood? Let me go look. It's going to be 1,060 kilogram per meter cube. So let me just write this down. Your density for the blood is 1060 kilogram per meter cube. That means our mass is going to equal to 1060 multiplied by 5.2 times 10 to negative 23. Negative 3. Which, let me plug that in. So what you get? Almost 5.5 times 10 to the 3 grams. So it's 5.5 kilograms. That means your weight is going to equal to your mass times gravity, which is your 5.5 times 10 to the 3 that we found, multiplied by your 9.8. So it's going to be almost 54 newtons. That means the percentage is going to be your 54 that we found, divide that by your 690 newtons. So it's going to be 0.078, which is 7.8%. Let's go check our work. Yep, so we got 5.5 for the mass. For the weight, we got 54 newtons, and we get for the percentage 7.8%. And again, just a refresher, your pressure is your force per area, like we talked about, which means it's your Newton per meter square. So let's say if we have a question, suppose the pressure acting on the back of a swimmer's hand is 1.2 times 10 to the fifth power pascals. This area of the hand is 8.4 times 10 negative 3 meters square. Determine the magnitude of the force that acts on it. Okay, so we get 1.2 times 10 to the fifth power pascals and 8.4 times 10 negative 3 meter cube. So this was example 2. Our pressure was 1.2 times 10 to the fifth power pascals, and your area was 8.4 times 10 negative 3 meter square. And we want to find the force that acts on it. And again, your force is your pressure multiplied by your area. Actually, let me just write this down. P equals F over A. That means your F equals PA, which is 1.2 times 10 to the fifth power multiplied by your 8.4 times 10 to the negative 3. So we should be talking about 1 kilo newtons. Is that right? Yep, 1 kilonewton. So that defines the pressure. Now, again, the atmospheric pressure at sea level is going to be 1.01 times 10 to the fifth power pascals, which we already defined. So let's say, so again, when you're looking at an object immersed in a liquid, when you look at the net force in the y direction, so this is your point 1. Make this bigger. That's your point 1, that's your point 2. Your force is going to be, over here is your P1 multiplied by the area. Force going on here is going to be your P2 minus P2 multiplied by your area. That means your sigma force is going to be your F2 minus F1 minus your weight that's going down there. The weight is going to be your mass times your gravity. At the point 1, it's going to be P1A, point 2, P2A. So you got your weight going down, you got your pressure force, buoyant force going up, and you got your F on your area with your first pressure going down. So that means your P2A equals your P1A plus mg, but we define m as your volume, your mass, your volume multiplied by your density. that means your and your density is defined as your area multiplied by your height. That means your P2A equals your P1A plus your rho AHG, which equals to P1 plus rho HG, and that's what we derived earlier. So let's do this question. Points A and B are located at a distance of 5.5 meters beneath the surface of the water. Find the pressure at each of these two locations. Okay? So your height, let me just go ahead over here. This is example 4. So your height is 5.5 meters. And we want to find the pressure on here. So your pressure is going to be P2 is going to equal to P1. Your pressure at point 2 is going to be your pressure at point 1 plus rho GH. Your P1, that's going to be your atmospheric pressure. Atmospheric pressure, which is again going to be 1.01 times 10 to the 5th power pascals. So your pressure, final pressure is going to be, at point 2 is going to be, 1.01 times 10 to the 5th power plus your water density, which is 1,000 kilogram per meter cube, multiplied by your gravity, multiplied by our height, which is 5.5. Plugging it all in. You get, I got 1.55 times 10 to the 5th power pascals. So it's 1.55 times 10 to the 5th power pascals. Now that brings us to Pascal's principle, which says that any change in pressure applied to a completely enclosed fluid is transmitted and diminished to all parts of the fluid in the enclosing walls. So supposedly you have a car over here that's parked on a car elevator. So how would that car move? So when you actually apply a pressure onto piston 1, we're going to call this piston 1 with the area 1, the force that's going in is going to be applied back on piston 2. So let me just go in to my notes. So we said that here's our little tube, and let's say make this, this is ugly. It's better. So you have a force going on F1 with an area A1 that's going in over here on a force F2. And let's say the water is right over here. So that's F2 going in with an area A2. And this is your height, which is going to have to be the same height as the other side. Now, we said that your P2A is going to equal to P1A plus rho VG, which again, your volume is your area multiplied by your height. That means your P2A is going to equal to your P1A plus rho AHG. And again, we canceled out all the areas. We've seen that earlier before a little while ago. So your P2 equals your P1 plus rho HG. Now, what is H or delta H? Let me actually just rewrite this down. Let me just write down basically what we're saying is rho G delta H. So what is delta H? Well, delta H is your height, which is going to be H2 minus H1. So it's going to equal to 0. So this whole term is going to go to 0. That means your P2 is going to equal to P1, which means that your F2 over A2 is going to equal to F1 over A1. That means your second force that needed is going to equal to your first force multiplied by the ratio of the areas. And that's basically what we just did, right? So your pressure at point 2 equals your first pressure plus your rho GH. Our H over here, our height, is going to be this one minus this one. It's going to be same height, so it's going to equal to 0. So F2 over A2 is going to equal to F1 over A1. That means your second force that's needed is going to equal to your F1 multiplied by A2 over A1. So let's take this as an example, right? We have the input piston has a radius of 0.0120 meters, and the output plunger has a radius of 0.15 meters. The combined weight of the car and the plunger is 20,500 newtons. Suppose that the input piston has a negligible weight, and the bottom of the surface of the piston and the plunger are the same level. What is the required input force? So we got a radius of 0.012 meters, which is going to be our A2, and the output plunger is A1, which is going to be 0.15 meter. So let me write this down. So your A1, and I think, what's example is this? This is example 7. So your A1 is going to equal to 0.1, well, not A1, I'm sorry. Your R1, that's your first radius, which is 0.15 meters. And your R2 is 0.012 meters. That means your A1, well, before was your area for that is going to equal to pi r squared, which equals to pi multiplied by 0.15 squared. And and for this one, your area, which is again your pi r squared, is going to be pi multiplied by 0.012 squared. And we got also the force F1, which is 20,500 newtons. So F1 is 20,500 newtons, and we want to find what the second force is. That's our double question mark. So your F2 is going to equal F1 multiplied over A2 over A1. So that's going to equal to 20,500 multiplied by pi A2. So this is A2, this is A1. So pi multiplied by 0.012 squared divided by pi 0.15 squared. Your pi's cancel out. So what you end up getting is 131 newtons. So your F2 equals F1 multiplied by A2 divided by A1, which is what we got. We got the second area from pi r squared, which we got the radius for the second one. Your first area is pi r squared. We got the radius from the first one. Again, your pi's cancel out, so you get 131 newtons. So basically, we actually looked at this also. We defined what the buoyant force is, and it was the mass multiplied by the gravity. And when you're talking about the mass, it's the mass of the displaced fluid, which is your rho multiplied by your volume. So your buoyant force, the magnitude of the buoyant force is going to equal to the displaced weight of the displaced fluid. So any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. So let's do another example, shall we? Here's example number 9. Now you got a raft that is made of solid square pine wood. Determine whether the raft floats and whether, if so, how much of the raft beneath the surface. Now your dimensions for the raft is 0.4 times 4 times 0.3. So your volume, and again, this is the question number 9 now. So your volume, your length is 4, your width is 4 meters, and your height is 0.3 meters. That means that your volume, actually, let me just do this. Let me just erase this one out. That means that your volume is going to be length times width times height, which is 4 times 4 times 0.3. So we should get 16 times 0.3, so it'd be 4.8 meter cube. That means your buoyant force is going to equal to rho multiplied by V multiplied by G, which is going to be 1,000 multiplied by 4.8 multiplied by your gravity, which is 9.8. So it is 40. So this is 10, 40, 4.8, 48,000, get 1 out, so it'll be 47,000 newtons. So your buoyant force is 47,000 newtons. That means the weight of the raft, now let's see how much the weight of the raft is. Whether it floats or not. Your weight of the raft is going to be your mass of the raft multiplied by the gravity, which equals to, let me actually get a different color on this. Let me get a blue color. So the weight of the raft equals your mass of the raft multiplied by your gravity, which is, we don't have the mass of the raft, but we do have the density of the wood, of the pine wood that we have, multiplied by your volume that we have, multiplied by the gravity. Now, the density for the pine wood, that's going to be where is our density table? For the pine wood is 550 kilogram per meter cube. So our density for this one is 550 kilogram per meter cube. That means your weight of the raft would be 550 multiplied by your 4.8 meter cube multiplied by your gravity, which is 9.8. And if you multiply all that, we should get 26,000 Newton. Now notice that the 26,000 is smaller than the 47,000. That means your buoyant, 47,000 force is bigger than your weight. So that means your the raft floats. If it's floating, because it's floating, that means your buoyant force is going to equal to the weight of the raft, which the buoyant force again is going to be your rho multiplied by your V multiplied by your G, which equals to the 26,000 newtons. But we want to see how much of it is under the water. So basically, our density of the water is going to be 1,000 multiplied by, let me just write this in red, it's going to be 4 times 4 times H, the little part over here that's immersed underwater. So let me just go this one. This is going to be 16H. Let me write down this one equals 16H. Multiplied by 9.8. That's going to equal to 26,000 newtons. That means if your height that we're looking for is going to equal to 26,000 divided by 1,000 multiplied by 16 multiplied by 9.8. So if you plug that in, so you get 0.17 meters. So only 0.17 meter is underwater out of the 0.3. Excellent. Great. Now, supposedly, I don't know, you're using a garden hose this time, right? So we talked about the density, which is mass unit volume, which means that the mass, again, is your density multiplied by volume multiplied by rho, and the volume is your area multiplied by your height. Now, your height is actually it's a distance, which your V equals your distance over time. Let me just write this down. Velocity distance, this is your time. That means that your distance equals velocity multiplied by time. That means your mass is going to equal to your rho multiplied by your volume, which is, again, your rho multiplied by your area. Again, this is density. Multiplied by your velocity, multiplied by your time, which both of these are your distance, right? And again, this is, so you won't confuse it with the volume, that's velocity. And this is your volume. That means your mass per time is going to equal to rho AV. This is going to be how many kilograms you have per second, which we call, and let me just, which we call your mass flow rate. So your mass flow rate is how much mass you have per time, kilograms per time. So let's say you have, I don't know, you got an opening over here that's going down. Now this one has a bigger area. This one has a smaller area. So you got a water flowing this way at V1 with a pressure P1, which this is going to be H1, that's your height. This is going to be your H2. You're going to have a V2 over here. This is going to be your A2, a different area than your area 1, which again, you're going to have a P2 going on there. So if you actually look at this, let me change the font on this. We can change the font. For M1 over, well, it's the same mass. So M over T for the first one is going to equal M2 M over T for the second one. Your mass per flow rate is going to equal to your mass per flow rate. Well, we go M1, M2 over T1, T2. That's for number 2. That means, let me extend this up. Your rho 1, V1. And again, your M over T is going to equal to rho AV. And let me just write that down. Density. That way you would not confuse it as pressure, and this is your velocity. Notice I don't have the wings on it like I did for the other one. So your rho multiplied by your V multiplied by your area, A1 is going to equal rho A2 V2. Now it's the same mass, so it's going to have to be the same rho. That means these two go away, which means your A1 V1 is going to equal to A2 V2. Now your A1 V1, actually let me get a different color. That's going to be your volume flow rate, which is, we give it the word Q, which is how much meter cube per second. So basically what we're saying for this and this is Q1 is going to equal to Q2. Well, our work is going to equal your sigma, your force multiplied by your distance. The net of all forces multiplied by your distance, which equals to, and again, your force your P equals F over A. That means your force, again, is your pressure multiplied by your area. So this is going to equal to your delta P multiplied by your area multiplied by your distance D, or height. Height is a distance, which, again, these two, that's going to form your volume. So again, this one's going to equal to P2 minus P1 multiplied by your volume. That means your non-conservative work, which is your E1 minus E2, is going to equal to 1/2 M1 V1 squared plus MGH minus 1/2 M2 V2 squared plus MGH. Actually, it's the same mass, so we can actually ignore the 1 and the 2 because it's the same substance. Now, and again, this came in because your energy is your kinetic energy plus your potential energy. So your kinetic energy plus your potential energy for the first one minus kinetic energy minus your potential energy for the second one. So 1/2 MV1 squared over 2 plus MGH1 equals 1/2 V2 squared over 2 divided by MGH2. That means your work equals your P2 minus your P1 multiplied by your volume, which equals to 1/2 MV1 squared
plus mgh minus 1/2 mv2 squared. Let me just write this down better. Plus mg minus mgh2. That means your P2 minus P1 equals is going to equal to 1/2 m v1 over rho, sorry, not rho, your volume. Let me just write this down better. It's going to be 1/2 mv1 squared over your volume plus your mg h1 over your volume plus minus your 1/2 mv2 squared over your volume minus mgh2 over your volume. We went and divided by the volume on all the sides. And again, your mass per volume, if you notice, we have mass per volume right over here, which means that's your rho. That's your density. That means your P2 minus P1 is going to equal to 1/2 rho V1 squared plus rho GH1 minus 1/2 rho V2 squared minus rho GH2. Well, let's organize them. Let's put all all the ones together and all the twos together. So what you're going to have? So you're going to have P2 plus 1/2 rho V2 squared plus rho GH2 is going to be equal to P1 plus 1/2 rho V2 squared plus rho GH2. And that's, ladies and gentlemen, what we call your Bernoulli's equation. Bernoulli's equation. And now let's go back over here and take a look at this. We've already done this. So in a steady flow, the velocity of a fluid particles at any point is constant as the time passes. Okay? So in an unsteady flow exists whenever the velocity of the fluid particles at a point changes as time passes. Now, your turbulent flow is an extreme kind of unsteady flow in which the velocity of the fluid particles at a point change erratically in both magnitude and direction. So a fluid flow can be compressible or incompressible. Most fluids are nearly incompressible. Fluid flow can be viscous or non-viscous, and an incompressible non-viscous fluid is called an ideal fluid. Now, when a flow is steady, we're talking about streamlines are often used to represent the trajectories of the fluid particles, and that's what we just showed a little while ago. So we've taken the mass of the fluid per second that flows through the tube is called your mass flow rate. It's your kilograms per second. So basically, and this is what we just did. We looked at the water flowing in a hose with two different openings, right? So you get your A1, your A2. You got is going at a V1, a V2, and coming out of V1. So basically your rho A1 V1 goes rho 2 A2 V2, which your volume flow rate is your area multiplied by your volume. And we went and defined, and we'll get back in just a second. We went and defined the equation, and we got Bernoulli's equation, which states in a steady flow, a non-viscous incompressible fluid, the pressure, the fluid speed, and the elevation of the 2 points are related by P1 plus 1/2 rho V1 square plus rho GY1, which we wrote H1, the height, equals P2 plus 1/2 rho V2 square plus rho G height 2. So let's say we have a question. A garden hose has an unobstructable opening with a cross-sectional area of 2.85 times 10 to the negative 4 meters square. It fills a bucket with a volume of 8 times 10 to the negative 3 meters square in 30 seconds. Finds the speed of the water that leaves the hose in an unobstructed opening and half as much area. Okay. All right, so this is example 12. All right, so let's take a look at the question. So the area is 2.85 times 10 to the negative 4. So that is your area 1, which is 2.85 times 10 to the negative 4 meter square. What else do we have? We have a volume of 8 times 10 negative 3. So our volume, or V1, which is going to be 8 times 10 to the negative 3. Meter cube. What else do we have? We got the time, which is 30 seconds. T equals 30 seconds. So find the speed and unobstructed opening. So part A. For part A, your speed, your Q is going to equal to your speed multiplied by your area. That means your speed is going to equal to Q over A. But Q is going to be, is how much volume you have per second. Again, it's how much meter cube per second, which is your volume per time, which means your volume is 8 times 10 to the negative 3 divided by your time, which is 30 seconds. So that makes it the flow rate, Q, not the flow rate, the velocity that's going in, V is going equal to the flow rate, which is going to be 8 times 10 to the negative 3 divided by 30, which is multiplied by your area, which is 2.85 times 10 to the negative 4. Let's plug this in. What I got was 0.936 meters per second. That's just for part A. For part B, you got your area is half as much. That means your A2 equals 1/2 A1. That means your V2 is going to equal to A1 over A2 multiplied by V1, which is from this one, we gather that A1 over A2 is going to equal to 2. So it'd be 2 multiplied by your 0.936. So your speed coming out is 1.87 meters per second. It's actually faster. And that would conclude chapter 14 for Physics 111. If you have any questions, email me at abunaemeh@gmail.com or at abunaem@uah.edu, or you can give me a call or text me at 256-348-1480. Thank you.